Hello. So in today's lecture, we're going to be looking at the Schrödinger equation and time evolution. So first, we're going to go through how we find that unitary time evolution operator that we discussed last time. So in the last lecture, we saw that the time evolution of a quantum system was given by a unitary operator acting on the state, and that was one of the axioms. So we just say that the time evolution is given by this unitary operator acting on the state. Okay, and we stated what that time evolution operator was, but I never went through how we actually got that. Okay, so we're going to go through that first. Now, this isn't a formal proof on how this operator comes to be, but it gives you an idea of where it comes from. Okay, so let's start off with what the Schrödinger equation is, and then we'll see how we get that operator. Okay, so the Schrödinger equation is a linear partial differential equation Okay, we'll get to what all that means shortly. That governs the wave function of the quantum mechanical system. Okay, so when I say wave function, previously I called that the state vector. Okay, so that's the same thing. It just depends on your perspective of the situation. So this is the state vector, as we had it before from the Hilbert space of the quantum system. Okay, so this equation is given by, this equation is given by minus I h bar. Okay, so you should be familiar with R, that's the unit complex number, h bar, that's just Planck's constant divided by 2 pi. Then we have d by dt of the state vector. So how does the state vector change in time? This is given by the energy operator, also called the Hamiltonian, acting on the state vector. Yeah, so the Hamiltonian acting on the state vector gives us how the vector changes in time. Okay, so this is written in vector notation. We assume we've got our Hilbert space that contains all the state vectors. We can write it like this. So that's if we're using this state vector jargon. This wave function, okay, so you might be familiar with that. The wave function is a different perspective on this. And instead of working with these vectors, like row vectors and column vectors for finite dimensional spaces, instead you work with wave functions. So those are functions psi of x and t. Okay, they also belong to a Hilbert space. Okay, but this is the Hilbert space of square integrable functions. Don't worry about that. It's just another vector space, but with functions, so complex functions. So with functions, you can add them together and you get back another function. You can scalar multiply them and you get back a function. You can also take the inner product. That was done in one of the homework problems. So you can form a vector space and a Hilbert space using functions. Okay, so there's no real difference between when we say state vector and when we say a wave function. Okay, so they're both from Hilbert spaces. They're both vectors in the Hilbert space. It's just a different way of looking at it. Okay, so the row vectors and the column vectors, those are reserved for finite dimensional systems. And then we have these functions for continuous systems, like particles moving around. Okay, anyway, so that's the difference between state vectors for finite dimensional Hilbert spaces and wave functions for infinite dimensional Hilbert spaces for particles and such. Okay, so if we look at these functions, the Schrödinger equation then becomes minus I h bar d by dt of psi x and t is equal to this energy operator. But if we're working with this function perspective, it's given by h bar squared over 2m d2 by dx squared of psi x and t plus v psi x and t. Okay, so it's given by this partial differential equation here. Okay, where this first term here, this corresponds to the kinetic energy of the particle. And then this one here with the V, that's the potential energy. Okay, so that's for continuous systems. We're not going to be looking at that. We're going to only be looking at the finite dimensional Hilbert spaces. Okay, so you'll be looking at this in another course. Okay, but this is just to let you know of the different ways of looking at quantum mechanics. So you can look at finite systems and continuous systems. Okay, so how do we get from the Schrödinger equation to that unitary operator that we saw last time? Okay, what we can do is rewrite this equation. So minus I h bar d psi by dt is equal to h psi. And this is very not rigorous at all, but let's just go with it. We can rearrange this and write it as d psi bar psi is equal to minus I h bar dt. Okay, so this is very messy. Okay, so again, it's not a formal proof or anything. It's just an idea of how we get that that operator. Sorry, I forgot the Hamiltonian. Dt. Okay, now we can integrate both sides, and then we get the natural log of the state vector is equal to minus RT over h bar times h. Okay, then we can plus some constant. Okay, then we can exponentiate both sides, and we get that the state vector is e to the minus RTH over h bar. And then when we exponentiate this constant, we get a multiplicative constant in front. But in this case, if we impose the initial conditions, it's going to be psi naught, the initial state. Okay, so that's it. Just if we let t be 0, we get the identity times the initial state. So that's just the initial state. And as we vary t, we get the new states after the time evolution. Okay, so once again, this is not a formal proof. Please don't take this as any proper mathematics, but it gives you an idea of where this time evolution operator comes from. So this thing in front here, that is our u of t that we had before. Okay, so this is just a very rough way of seeing where that operator comes from. Okay, so let's have a look at an example of how we use this. Okay, but before we get to that, I just want to go over briefly what we've covered before with eigen decomposition. Okay, so in the section on Hermitian matrices, we showed that we could write it as a sum of the eigenvalues times the corresponding projection operator. Okay, so we'll briefly go over that and then show how we can use that to solve these time evolution problems. Okay, so a brief aside on eigen decomposition. Okay, so we did cover this before, but I just want to go over it again because we're going to be using it for this example. Okay, so if n orthonormal eigenvectors, let's call them 1 to n. Again, the 1 to n, those are just labels. Okay, of a Hermitian matrix are chosen and written as the columns of the matrix U. Sorry, columns. U. Then we can write A as A equals U B U inverse, like we had before. Okay, so that's the diagonalization of A, or yeah, we had this as one of the properties for Hermitian matrices. We can write it as A is equal to the sum from I equals 1 to n of lambda r, where that's the eigenvalue, and then we have I outer product. Remember, that was the projection into that eigenspace. So this is the eigenvalue, and this was the projector to the eigenspace. Okay, so we could write it in these two ways. Now, we're going to be using both of these methods to solve the given problem. The first way, using this UDU inverse, that's going to be left as a homework exercise. And then the second way, I'm going to go through now. Okay, so recall that we have this A can be written like this. And if we want to take the function of A, remember that is the same as after diagonalizing, taking the function of the eigenvalues. Okay, we showed that previously. So this is equal to the sum, I equals 1 to n, f of lambda r, I times r. Okay, so this is very similar to what we had before when we took f of a diagonal matrix D. We had the diagonal elements running along the diagonal, and then if we take the function, it's going to be f of lambda 1, f of lambda 2, and so on. Okay, very similar to what we have here. Okay, so we have the function of the eigenvalue, and then we have the same projector. Okay, and this is called, so altogether, this bit here, we call this the spectral theorem. Yeah, and just a note on this spectral part, the set of possible eigenvalues for a given operator we call the spectrum. Okay, and if you think about it in terms of quantum mechanics, those are your expected values for a measurement. So if you measure something, you have to get one of those values. That is the spectrum. Okay, and then this is the spectral theorem. Okay, so let's go through the example. Okay, so given H is equal to 4, 2, 2, 1, and psi naught is equal to 1, 0, find the time evolved state, psi. Okay, so after some time t, what does the state end up being? Okay, and then just for this example, I'm going to set h bar being equal to 1, just so that we don't have to write that repeatedly. Okay, so first things first, we need to find the time evolution operator and then act it on psi naught, and that's how we get psi. So we need the function of the Hamiltonian here. Okay, we need to exponentiate it. That's difficult because this Hamiltonian is not in diagonal form. So we need to make it into diagonal form. Okay, so let's call this part 1. That's using this matrix diagonalization approach here. So you're going to be doing this for homework. So part 1. We're given h. So u of t, remember, is e to the minus rth, where we're letting h bar equal 1. Okay, so then this is going to be like that p inverse. So it will be p e to the minus rt d e inverse. Okay, so that is where d is the diagonal form. And then once we have this, we can write psi as u of t psi naught. Okay, so then that is just matrix multiplication. So this is using the p inverse way of diagonalizing the matrix. Okay, and then you're going to end up with the matrix. You multiply it onto psi naught, and then you get your psi. Okay, so you're going to be doing that way for homework. I'm going to be using the spectral theorem way to show you an alternate. Okay, all the ways are perfectly valid. It's up to you which way you want to do. Okay, so let's look at part 2 using the spectral theorem. Okay, so to use the spectral theorem, we need to first find the eigenvalues and eigenvectors. So that's pretty much the same as using part 1 to find the U inverse or the P inverse. Okay, so finding the eigenvalues and eigenvectors. And eigenvectors. Okay, so remember how to do that. We find the determinant of the operator minus lambda times the identity. We set the determinant to 0, find the eigenvalues, and then find the corresponding eigenvectors. Okay, so we know h is 4, 2, 2, 1. Okay, so we need to find the determinant of 4 minus lambda, 2, 2, 1 minus lambda, and we set that to 0. Yeah, we want the determinant to be 0. So we're going to get 4 minus lambda, 1 minus lambda minus 4 is equal to 0. We can expand this out, and we're going to end up with lambda squared minus 5 lambda is equal to 0. So lambda minus 5 is equal to 0. So we get 2 eigenvalues. Lambda 1 is 0, and lambda 2 is 5. Now, just a note, the eigenvalues can be 0. That's fine, but the eigenvectors can't be 0. So remember, we excluded those from the set of eigenvectors. Okay, but eigenvalues, they can be 0. Okay, so let's find the eigenvector corresponding to lambda 1. So if lambda 1 is 0, we're going to end up with the following eigenvector equation. Once we take everything over to one side, we're going to end up with 4, 2, 2, 1 times some xy we don't know is equal to 0, 0. Okay, so that's the eigenvector equation with the right-hand side taken over to the other side. So this was like h minus lambda r, times v is equal to 0. Yeah, so I just took everything over to one side, and then we get this equation here. Okay, so the first row we see is a multiple of the second. So the 4, 2, and the 2, 1, they're just multiples of each other. So the rows are dependent, so we can just use one of them to solve the problem. So this gives us 2x plus y is equal to 0. 2x is equal to minus y. One of these variables is free. The other one is fixed by this equation. So if we let x be 1, you can let it be anything. So let's just say it's 1. Then that means y is equal to minus 2. Okay, so this gives us the first eigenvector 1. And that is given by 1 minus 2. And remember that we like these to be normalized when we're working in quantum mechanics. So this is going to be 1 over root 5. 1 over root 5. Okay, so that is the first eigenvalue and the first eigenvector. Let's find the other one. So that's lambda 2 is 5. Okay, so again, we get the equation minus 1, 2, 2, and minus 4 times xy equals 0, 0. Okay, again, these rows are dependent, so they're just multiples of each other. So one of the rows we can use to solve the problem. So that means one of the variables will be free. Okay, so let's use the first one. So minus x plus 2y is equal to 0. X is equal to 2y. Again, one of the variables is free, one of them is fixed by this equation. So let's say y is equal to 1, and in that case, x will then be 2. Okay, so the second eigenvector will then be x is 2, y is 1. We need to normalize it, so we get 1 over root 5. Okay, so we have our 2 eigenvalues and our 2 eigenvectors. If we use the spectral theorem, so we can use the spectral theorem, spectral theorem to write h is equal to the first eigenvalue, that's 0, and then the first projector is just 1, 1, and everything's fine because we have normalized it. Okay, so that's fine there. Plus, the second eigenvalue is 5, and then the second projector, again, everything's fine because we have normalized it. Now, you might say 0 times this is just going to be 0, but leave it there. Okay, so we don't want to not write it down just because there's 0, because when we take the exponentiation of this Hamiltonian, we will see that the 0 actually does affect the result. Okay, so even if your eigenvalue is 0, rather just write it as 0 times the projector. Okay, so you'll see what I mean right now. So e to the minus I h t, that's going to be e to the minus r 0 times t, and then the first projector, plus e to the minus r5t times the second projector. Now we see that the 0 in the exponential here, that's going to make this a 1. Now, if we left it out, then we wouldn't have that term. Okay, so please write down all your eigenvalues, even if it's 0. Okay, so I hope you see that if you didn't write that 0 there, you might have not written down that term. Okay, so e to the minus rth is going to be a 1 here, so a 1, and then the first projector plus e to the minus r5t times the second projector. Okay, good. So we've got this now. now we can write this times the state vector, which was, if we go back up here, 1, 0. Okay, so now there's two ways of continuing from here. We can either substitute the projectors, the matrix form of those projectors. We can substitute that and then do matrix multiplication. Or the alternate way, which we're going to do a bit later, is we're going to write this initial state as a linear combination of the eigenvectors and then proceed from there. So we'll see that's actually quite a bit easier. Okay, but let's first do it the matrix way, where we substitute the matrix form of the projectors and then use matrix multiplication. Okay, so we've got this, and what we want is psi is e to the minus rth times the psi naught. Okay, and to do that, where psi naught is the column vector, we need this e to the minus rth to be a matrix. Okay, so we can substitute the row and column vectors for the 1 and the 2 state vectors, and then write everything as a matrix. Okay, so let's do that. So this is equal to, I'm going to drop the 1. So we have the first state vector as a ket. So that's going to be 1 over root 5. And then the first state vector, if we look back here, that was 1 minus 2. Okay, so that is 1 minus 2 times, and then the bra form of it, so that's the row vector form, that was 1 over root 5, 1 minus 2. Remember to do the complex conjugation if we have any complex numbers there. Okay, so that's the first part, plus e to the minus r5t, and then the second eigenvector, that was 1 over root 5, 2, and a 1. Okay, so we've got 1 over root 5, 2, and a 1 as the ket form, and then we need the bra form, so that's 1 over root 5, 2, and 1. Okay, and then it was all of this times the 1, 0 initial state. Okay, so 1 over root 5 times 1 over root 5, that's 1 over 5. So we have 1 over 5. And then the column times the row, that's going to give us a matrix. That will be 1, minus 2, and 4. Plus, and then again, the 1 over root 5 times 1 over root 5, that's 1 over 5. E to the minus r5t. And then again, we're going to get another matrix. So 2 times 2, that's 4. 2 times 1, that's 2. 1 times 2, that's 2. 1 times 1, that's 1. Okay, and then all of this times 1, 0. Okay, now the 1, 0 we can distribute inside. So we're going to get 1 over 5. 1 minus 2 minus 2, 4, not minus 4. Times 1, 0, that's our initial state. Plus 1 over 5. E to the minus r5t, and then we have 4, 2, 2, 1 times our 1, 0. Okay, so this is quite easy to do now. So this is 1 over 5. Then this is going to be 1 if we do the dot product there, and then minus 2. Plus 1 over 5 e to the minus r5t. Then we're going to get 4 and 2. Okay, so we'll just leave it like this for now. That's fine. Okay, so we could add this together, but then the components get a bit complicated with this exponential here. So we'll leave it like this and refer to it later. But this is the general idea of what we need to do. So given the Hamiltonian, we need to exponentiate it. So we can use the spectral theorem to do that. because exponentiation is just taking the function of the operator, and then that just goes to taking the function of the eigenvalues, and then the projectors stay the same. Then the projectors, we can write that using the normalized eigenvectors. Remember, the kets are column vectors and the bras are row vectors. Multiplying them together gives us matrices. And then the matrix times the state vector, which is a column vector, gives us another column vector. And then that's our new state. Okay, so everything's relatively easy once we find the projectors and the eigenvalues. Okay, so this way is perfectly acceptable. However, I do want to show you another way that might be a bit easier to work with. And that involves taking the state vector over here. Yep, so taking the state vector and writing it using the eigenvectors. Okay, so this 1, 0, we can write it as a linear combination of the eigenvectors of H. Okay, because the eigenvectors span the space, we can use them as a basis. In fact, we can use them as an orthonormal basis. Okay, that was one of the properties of Hermitian matrices. Okay, so please go back and review that if you need to. Okay, so we've got the state vector psi naught. We're going to write it as a linear combination of the eigenvectors of H because they form an orthonormal basis. Okay, so let's do that. Okay, so psi naught is equal to 1, 0, and we would like to write it using the eigenvectors. So it's going to be C1, some basis expansion coefficient, times the first basis vector. That will be 1 minus 2. So times 1 over root 5, 1 minus 2, plus C2 times the second basis vector. We go back here, that will be 2, 1, and then the 1 over root 5. So 1 over root 5 times 2, 1. Okay, so this gives us a system of equations that we can then solve for C1 and C2. So 1 is equal to 1 over root 5 times C1 plus 2 over root 5 times C2. That's if we look at the first components. If we look at the second, we're going to get 0 is equal to minus 2 over root 5 C1 plus 1 over root 5 times C2. Now we have two equations, two unknowns. We can solve for C1 and C2. That's quite easy to do. Let's go through it. So if we look at the second equation, we're going to get that 1 over root 5 C1 is equal to 2 over root 5 C2. Other way around. This is 1 over root 5 C2 is 2 over root 5 C1. Okay, so C2 is twice C1 if we cancel the 1 over root 5 on both sides. Okay, we can then substitute this back into the first equation, and we're going to get 1 over root 5 C1 plus 2 times C1 in place of C2 times 2 over root 5 is equal to 1. Okay, so we're going to end up with 4 plus 1 over root 5, so that's 5 over root 5 C1 is equal to 1. So C1 is going to be root 5 over 5. Okay, and if we times top and bottom by root 5, we can write this as 1 over root 5. Okay. And then if that's C1, then C2 is twice that. So C2 is going to be 2 times root 5 over 5. or 2 over root 5. Okay, so those are the expansion coefficients. Let's substitute them back into that original equation we had. So psi naught, that was 1, 0, is equal to C1 is 1 over root 5 times that. So it's going to be 1 over root 5 times 1 over root 5 times 1 over root 5. And then it was 1 minus 2. That was for the first state vector, plus 2 over root 5 times the 1 over root 5. And then we had, it was 2, 1, 2, 1, yep, for the second state vector. Okay, but this is similar to what we had before, working with vectors like this. But instead of that, I'm going to replace this 1 over root 5, 1 minus 2 with the first state vector. And I'm going to replace this 1 over root 5, 2, 1 with the second state vector. So psi naught is equal to 1 over root 5, 1 plus 2 over root 5, 2. Okay, so instead of writing it as column vectors, I'm writing it in that Dirac notation or that bracket notation. We'll see that this makes it a bit easier to work with. Okay, and just as a homework exercise, check that this is normalized. Check that this is normalized. Okay, so it's a very, very quick check. But please do check that your state vectors are normalized to avoid any scaling issues. Okay, so we've got our psi naught. Now we need to time evolve it to get psi. So that is e to the minus rth. Again, I'm setting h bar to 1 just to avoid it here, times psi naught. Okay, so this is e to the minus rth times by 1 over root 5, 1 plus 2 over root 5, 2. Now, the nice thing is, if we have an operator like this, h, or a function of the operator, in this case, e to the minus rth, acting on an eigenstate or eigenvector like this and like this, what we do is we replace the operator inside the function with the corresponding eigenvalue. So if we look back at h times v is lambda v, then if we have f of h acting on v, then this is f of lambda, again acting on v. Okay, so this is similar to what we had before with the spectral theorem. Okay, so in fact, we can write this as 1 over root 5, 1, because remember that first eigenvalue was 0, e to the 0 is 1. And then we have plus 2 over root 5, e to the minus r5t on 2. Okay, and then the problem is solved. We have the same answer that we had before. If we look back here to the previous one over here. Okay, if we just include the normalization of 1 over root 5, then this can be written as 1 over root 5, 1. Again, if we just include the normalization, because 1 minus 2, that's the first eigenstate. And then 4 over 2, that is twice the second eigenstate. So this will be plus 2 over root 5, e to the minus r5t, and then 2, 1, that's the second eigenstate, so that's 2. So you see we get exactly the same answer here. Okay, just by using the fact that the function of an operator operating on an eigenstate is the function of the eigenvalue operating onto the eigenstate. Okay, but maybe you forgot that. What happens if we want to do this without that knowledge? So let's say we don't know that that's true. What we could do instead, so let's just put a dotted line here. So instead, we could write this e to the minus th using the spectral theorem. So let's do that. So if we use the spectral theorem with that, it's going to be, we had it over here, 1 times the first projector plus e to the minus r5t times the second projector. Okay, so it's going to be 1 times the first one, but let's just write that as 1 plus e to the minus r5t, and then the second projector. So that's writing it out like we did before with the matrices. But instead of explicitly putting in the matrix entries, we're just leaving it like this in the bracket notation. And then this is being multiplied onto what we had there. So 1 over root 5, 1 plus 2 over root 5, 2. Okay, now we do the multiplication, because remember this outer product, that's just the matrix. The ket, that's just a column vector. We can do the multiplication. Okay, so we're going to have 1 as the projector times 1 over root 5, 1 plus 1 times 2 over root 5, 2. Then we're going to have e to the minus r5t, the second projector, times 1 over root 5, 1. And lastly, e to the minus r5t to 2 times 2 over root 5, 2. Okay, so that's multiplying everything out. Let's neaten it up a bit by taking all the constants to the front. So we're going to get 1 over root 5, 1, and then times the ket 1. But notice that when we take this outer product times the ket, it becomes a ket times an inner product. In other words, it becomes the projection onto 1. Because remember, the inner product, that finds the components along that vector, in this case, the vector 1, and then we scale it by that vector. Remember, that was the vector projection. Okay, so outer product, in this case, it's a projector, so that's exactly what we want, times the ket. It did the projection for us there. Okay, so everything is working as expected. Okay, plus 2 over root 5, 1 in a product with 2. Again, we've got that projection going on there. Plus 1 over root 5 e to the minus r5t, 2, and then in a product with 1. Plus 2 over root 5 e to the minus r5t, then we have 2 in a product with 2. Okay, so this looks a bit messy, but remember that the eigenvectors are orthonormal. Okay, we've already shown that we could normalize them. That's easy to do. But the important thing here is that they are orthogonal to each other, which means the inner product of 1 with 1, they are normalized, so this is just 1. The inner product with 1 with 2, remember they're orthogonal, so the inner product is 0. 2 with 1, they're orthogonal, so that's 0. 2 with 2, they're normalized, so that's 1. So all of the mixed inner products, the 1 with the 2 or the 2 with the 1, they go to 0. And we're left with 1 over root 5 times 1 plus 2 over root 5 e to the minus r5t to outer product with 2. Oh, sorry. not outer product. The outer product goes away once we do the projection. So that's just 2, which is exactly the same as what we had before. Okay, so you see there are various ways of going about solving this problem. So let's just recap. We go right back to the top here. Okay, so we want to find the time evolution of this initial state, 1, 0, with this Hamiltonian H. Okay, so you can either diagonalize the Hamiltonian using PDP inverse, such that taking the exponential is a bit easier, because exponentiating a diagonal matrix is just exponentiating the eigenvalues along the diagonal. Okay, so you can do it this way. That's perfectly fine. You'll get exactly the same answer. Okay, and then that was for homework. Or you could use the spectral theorem and work with eigenvalues and projectors. So we find the eigenvalues, and then to find the projectors, we need to find the normalized eigenvectors. Okay, so 1 and 2. Then using the spectral theorem, we can write out the Hamiltonian as such, where we have lambda 1 times the first projector plus lambda 2 times the second projector. And again, note that if your eigenvalue is 0, please still write it. We don't want to be leaving out important terms. Then the function of the Hamiltonian, in this case exponentiation here, is just applied to each eigenvalue in a very similar way to how you exponentiated the diagonal matrix. Okay, then the exponential form is given by this. Okay. And noting that the outer product, they just form matrices, we can substitute the vectors, the column vectors and the row vectors, we can substitute that to end up with the matrices. So that's what we did here. We formed the matrices with the eigenvectors, we multiplied that onto the initial state vector, and we've got our answer here. Now, you can either write your answer in this column vector form, or you can write it in terms of this direct notation form, okay, just by looking at what the final results are. Okay, so you can see how we got from this left-hand side to this right-hand side. Okay, so you can do it like that by directly substituting the vectors and the matrices. Or another way is to write the initial state as a linear combination of the eigenvectors, because we know that the eigenvectors are orthonormal and they form a basis. So of course we can use it as a basis here. So we find the expansion coefficients, C1 and C2. That's very easy to do there. And then we end up with, here we go. We end up with the same vector, but now written in terms of the eigenvectors. How does that help? Well, if we write the state vector in terms of the eigenvectors, then this operator acts on the eigenvectors very easily using this on the right-hand side. So the operators act very easily on the eigenvectors. Okay, so that is a good reason for why we used that particular basis. Of course, you can use other basis. It doesn't change your answer. However, using this particular basis does make things quite easy. Yeah. Just a note on that. If we look back up here, you see here we used the standard basis, the 1, 0, 0, 1, and we got the same answer in the end. Okay, yeah. So we have the function of the operator acting on the eigenstates. In this case, the operator is just replaced by the corresponding eigenvalue. So the first eigenvalue was 0, so it just became e to the 0, which is 1. In the second case, the eigenvalue was 5, so the h was replaced with 5. Yeah, and we get the same answer as before. Now, if you don't remember that, that's perfectly fine. You can still get the answer, even if you forget that fact. So instead of directly applying the operator, we write the operator using the spectral theorem. In terms of projectors, we multiply these projectors onto the eigenstates. And then we do need to know that the basis is orthonormal. So the inner product of the eigenstate with itself will be 1 because they're normalized. And if they are different, then it's 0 because they are orthogonal. Then after a bit of cleanup, again, we get the same answer. Okay, so any of those ways work perfectly fine. But the way that I recommend is this over here. Okay, so this way over here, using this fact that I put in a box here. Okay, so I think that is the easiest way to approach these problems. Okay, but of course, you can do whichever way you prefer. You'll get the same marks in the end. Okay, and then please remember to do this first way over here. Oh, sorry. Here, using the PD P inverse diagonalization approach. Try it out that way for homework. Again, you should get the same answer. Okay. If you have any questions on this, please don't hesitate to email me. I'll get back to you as soon as possible. If you would like to meet in person to go over anything, you can visit me in my office. All those details are available on the course webpage. Okay, so just a note for next week. Next week, Wednesday, I'm not going to be available for the tutorial. Okay, so if you do have any issues, please see me on the Monday if you want to go through it in person, or you can email me throughout the week. And note that the week after, we're having class test 1. Okay, and that will be on the Wednesday in the computer room, the same place that we have the tutorials. Okay, and remember, it is on theory and the computational part. Okay, so you should be comfortable solving problems on paper and then solving them with those Python programs. Okay, if you have any questions on that, please, again, just email me. Yeah, and I'll see you next time.